Hi everybody. Okay, I'm going to make sure my mic is working. Okay. So earlier today I solved this problem, which I actually found because my friend and I were doing some CF lockout. I feel like the solution is pretty elegant, and it focuses a lot on combinatorics, which is something that I'm working on. So I wanted to share my solution with you guys. Okay, so this problem essentially is based this way. So you have n seats and you have k aisles. Basically, let's say we have this configuration of seats. The circle will represent an aisle. And then just like this configuration, which is also described here in the input, which is a 3-3 seat layout. We are given this idea of an inconvenience, which is for each seat, it's the distance -1 from an aisle. So, in planes, like there are these things called aisle seats, window seats, and an aisle seat is one that's right next to an aisle. So like, let's say you wanted to get up and do something, this would cause an inconvenience of 0 to other people because you are right next to the aisle. So these aisle seats have an inconvenience of 0. The ones right after have an inconvenience of 1. And the furthest ones, which are also known as the window seats, not that that's an important terminology, but those have a contribution or inconvenience of 2. So obviously this problem, we have a very interesting plane, right? So we can have up to 10 to the 9 seats, and we can also have up to 10 to the 5 aisles. And obviously we are also guaranteed that k is less than n, which is pretty helpful. And while we want to find the minimum inconvenience over all different variations of the seats, and we want to count how many different variations lead to the minimal inconvenience. And just note that the sum is just the sum over all inconveniences, but we want to take the number of ways mod 998244353. Okay, so as this is a math problem, we want to make more general observations rather than just, try to assume it's some sort of algorithm, DP, that type of stuff. So let's break down this problem into 2 parts. So part 1b, the calculation of the total, or just total sum. And then the second part will be exactly how many ways there are. So let's try to make some sort of observation about just how this alignment of seats work, arrangement of seats work. So let's say we have 2 aisles and we have 4 seats that we want to place, 4 squares. Now what's the optimal way to place these seats? Well, obviously we want to start with the zeros, right? The inconvenience of zeros. So we can start by placing 2 squares here in the middle, because we know that these both have an inconvenience of zeros. And then we can take in the outer layers, and these also have an inconvenience of 0. Well, now let's pretend that we no longer want 4 seats. We want 5. The first 4 obviously remain the same. They do not change places. But now let's look at the 5, the 5th seat. Well, you can place it here, or you know what, let's change color. Let's make it green. Well, you can place it here, right? This is a possibility. It would have an inconvenience of 1. You could also place it here. Sadly, it would also have an inconvenience of 1. Or you could also place it here, and also has an inconvenience of 1. So I will just be directly sharing the pattern that we can make based off of this. As you can notice, it appears that there may or may not be some set amount of seats that we can place per inconvenience. So going back to this case, pretend we now want 9 seats, right? Or let's not put 9, let's put 8. 8 seats. I will quickly erase these, right? Oh, got that. Yeah. So with 8 seats, what we will do is obviously we can place one here. It would have an inconvenience of 1. We can place 2 in the middle here. So they would also have an inconvenience of 1. And we can place 1 back here. It also has an inconvenience of 1. So for this case, you may or may not have noticed that it appears for every 4 elements, so every 4 seats, we place down a seat that has a new inconvenience. We place down seat, we'll just abbreviate with S, with new inconvenience. So this is actually a pretty core observation if we want to find the sum. Because, you know, if we know how many inconvenience, like after how many seats we place, there's a new inconvenience, we can quickly derive the sum by using some simple arithmetic, because we can just, you know, we can find the full inconvenience, right? So we can find some value v such that there are exactly max inconvenience seats for these v values. So what do I mean by this? Like for the case 8, right? The max inconvenience seats would be 4, and the v values would be 0 to 1. So there are actually 2 values. So we get this value v, and then we notice that it seems like to find the sum of all contributions, it would just be 4 times 0 plus 4 times 1 plus 4 times 2, etc., all the way to 4 times v, at least for this test case. And this can just be simplified down to 4 times v times v plus 1, and all of that over 2. So then that just ends up as 2 times something, blah blah blah. So we don't need to worry about that. And then after we find this, we can find how many remaining seats there are. So R, let's denote that as R. So that's like the remaining seats with the max filled inconvenience plus 1. And then we can simply just add R times this new max to our answer. Okay, so exactly how do we find the max inconvenience seats, and how will we find V and R? Well, it turns out there's a very simple observation. First, we can see that given k aisles, there can be 2 seats placed between 2 aisles that would have the same inconvenience. And then there can be 1 placed out on the right border and 1 placed out on the left border. So there are obviously k minus 1 middle, and then there are plus 2 of the outer areas. And there would be 2 times k minus 1 total seats in the middle sections. And this just simplifies directly down to 2k. Okay, so we know that there are 2k seats per every new inconvenience. So then, to find the maximum, all completely filled inconvenience, that would just be n over 2k, take the floor of that, and then subtract 1. So this is like the, full filled, so let's just name it like the floor of like, FT, why not? Just call it FT, represent that. And then let's just have like the ceiling, or ceiling, CT, be equal to like n over 2k plus 1. I forgot if this is even useful, but we will see. Okay, so we now know FT. We now have FT. And now we want to find the remainder. So what would R be? Well, you see, we already know the maximum value, and we also know what FT is. Or no, sorry. We know FT, which is the maximum value, and we also know the maximum inconvenience, which is actually just 2k. So if I remember correctly, the remainder is just n minus ft plus 1, right, ft plus 1 times 2k. So let's just quickly walk through an example for our good old case for 4.1, right? Or no, let's just take 4.2. Yeah, 4.2. Actually, 4.2 is not a good one. 5.2. How about 5.2? So 5.2. We have these 2 aisles. We already placed these down. 5 over 4, the floor of that is equal to 0. The remainder would be equal to 5 minus 1 times 4, and that equals 1. So we have a remainder of 1. And then we can do some sort of operations with that. Okay, so now for the sum, I think this should also be fairly easy. So back to our earlier derived equation. So, well, not completely derived, but we have this. Right, we have that is a pretty bad outline, but we have this. V represents our maximal value. 4 represents the maximal, like, something. So our final equation for the sum, based on what we have, is just remainder times the ceiling, because we can just do CT. Yes, V times CT plus V times FT times FT plus 1 over 2. Yeah, looks correct. And just note that this is an R, and this should not be a V, or yeah, this should not be a V, and this should just be the 2K. This should be 2K, sorry. Okay, so now let's try to implement this, because why not? We can also just double check our work along the way. So we have ln n, k, cn, n, and k. Okay, so at least based on what we have defined this to be, ln ft would be equal to the floor of n over 2k minus 1. Oh my. You know what, let's just define ln g as 2 times k. Because g would like represent, groups, like max and convenience, Let's quickly switch these out to double. Ln double actually would probably be better. Ln double. Also, I apologize if there's like background noise. It's just like outside, I will probably work on trying to fix that sometime, but for now, that is not super important. Ln ct would be equal to the CO of ln double. Oh man. Double n over ln double g, and we can also minus 1, because why not? Okay, so now let's find the sum with, or let's find the remainder. Yeah, I almost forgot that. So ln rem is equal to n minus ft plus 1 times 2k, 2 times k, or g. Shoot, I keep forgetting that. And ln sum is equal to rem times ct plus 2k g times ft times ft plus 1 over 2. And we can just see out the sum. So okay, let's double check just to make sure. C-line takes a bit to load sometimes, so we'll give it a second. Also probably because my computer is like just lagging due to all of the things that are running on it. So yeah. Okay, it appears that this works very well. Okay, so now we are on to the relatively, more difficult part of the entire solution. So part 2. We now want to know the total number of, assignments. Number of assignments. Okay, so how are we going to find this total number of assignments? Let's start with a relatively more basic case first. So, or let's just split this down first, right? So you know that we have k aisles. We know that there could potentially be some stuff in these aisles and also outside. We have some number of elements, so we have like some number to insert, number to add. And we know that we can add these elements somewhere here. We can add them in all these like separate areas. So now let's break this down a bit. There will be 2 major cases. One where the sum is equal to 0, and one where the sum is greater than 0. Okay. So why is the sum equal to 0 a special case for us? Well, this is because if you take a look at our code, right, the ft value will actually just be, it will be 0, right? So that means basically every single element is considered a remainder, if I am not wrong. Wait, am I wrong? So let's see. So floor ft equals 0, so that would be 1 times g, 2 times k. Let me think about this for a second. Sorry, I need to quickly just double check that my logic is logicking. Might not be, so we need to verify that, There is also actually a special case we can handle when the remainder is just 0, because that means that we know there's only one valid solution. So I will add that in right after I check this. Yeah, the remainder is equal to 3, right? So we know that there are 3 chairs. Ft after dividing should be 0 plus 1. G should be 2 times k, but that should be 4. Interesting. Oh yes, because that would be negative 1. So after you add 1, that's just 0. So the remainder is just 3. Okay, and as I said, if the remainder is just if the remainder is just 0, then if remainder is equal to 0, we can just handle the special case and just see out 1 and return. My earbuds ran out of battery. I don't need them anyways, so I'm just gonna put them away quickly. Yeah, cool. So when the sum is equal to 0, we just have like these empty aisles. We have these empty aisles, nothing in between them. So obviously this is a bit of an issue because we can't just have 3 elements be like this. They can't just be placed like that, right? So we actually need to quickly define that the only extra elements that we want to consider placing, so like the extra elements, should be equal to remainder minus k plus 1. This is because we want there to be at least one filled element per aisle, so this way we can continue applying operations on these aisles. And there's going to be a more specific case when we are dealing with this, which I will be explaining very shortly after we start covering what happens when the sum is greater than 0. Okay, so when the sum is greater than 0, we know that there is already going to be some predefined layer of nodes, right? So here the predefined layer is 0. We are on to consideration of the layer of 1. So let's say we have 3 extra elements. We want to know how to place these elements into this array, or just this current layer, right? So let's split this down. We know that there are, between like these 2 nodes, right, there are 2 slots that we can insert, but the issue is that just inserting into one slot makes no difference from inserting into the other slot. So we actually want to make that clear when we do the operations when we do the calculation on the middle. And on the outside, it's also quite interesting because we can either place one here, choose to not place both, etc. And we realized that perhaps because k is less than or equal to 10 to the 5 per test case, we can simply just use some combinatorics with some casework, right? So what we can do is or actually, let's merge this, right? Let's merge this. So this will be parts where we start to merge. So we will start to merge these two cases together. So for int I is equal to 0, I is less than or equal to 2, because, there can be 0 to 2 insertions on the borders, plus I. And on the inside, we want to consider the number of pairs, because they are often a lot more easier to consider. I will actually also save some space because there is going to be a bit of casework that we want to consider. So for int j is equal to 0, j is less than or equal to the remainder, so the rem, the rem minus I over 2, right? Because that represents how many total pairs we can have. We want to increment j. Okay. So back into the general case, we now have to consider when is such a pairing valid. So when do we know if we can have j pairs or not? Well, the first case is if, let's see. The first case is if there are how do I say this? Okay. So before we actually consider this, I forgot that I actually left out something very important, which is given these amount of pairs, we actually need to calculate how many singles there are. So the amount of singles that are left is just equal to so it'd be remainder minus I, because we want to take out these extra elements that we placed on the side, and then minus 2 times j. These will represent the number of singular elements we have. And this is actually crucial because we realize that if we want an element to be single, then it must not intersect with some other pair, right? So let's say we have these are all aisles, right? Then if we want to choose this aisle to be singular, then it must remain singular, right? Because we have as single elements, you can't just add another element into this aisle. So the first case that we can knock out is if the count of singular is, or I guess we can combine this. Because we know that pairs and singles cannot go together, it would just be if s plus j is greater than k minus 1. Oh, why did I draw an e? K minus 1, then we continue. Alright, so that is one of the cases that we have. The other case is if, because somehow s can become a negative value, so we also need to check if s is less than 0. We also want to continue. And finally, just as an extra check, we want to make sure that all these elements actually add up to the remainder. So if s is remainder, then we also take. So now this is probably the most, consuming, I guess, casework-ish combo bash part, which is the answer, right? For each case, we add them up. We want to count how many, choices we have. And the first is which exact groups are we going to choose, right? So that would be K minus 1 choosing J, and then we want to multiply that by selecting the J out of the J plus S to be pairs. And want to multiply the potential case to 1 because, one element alternate. So it's just I is equal to 1, then apply 2, otherwise multiply by its case, right? 2, otherwise 1. And yeah, now we want to consider what's so special about, this. And also, just to make this part a bit more clear, this is like the general case, so I want to change the color to red because it's more about this side of the equation. And honestly, this part is actually pretty simple to cover. Basically, because we were already assigned, oh no, why is it red now? Okay, so basically, because we have already assigned that one extra element there, and we know that there's a type remainder, if either just break, yeah. Otherwise, we go through and then, I'm actually pretty sure we just do like some sort of direct choose on like the middle portion. So, you know what, we might as well just directly handle that, I suppose. Because we'd have these amount of remainders, we would have, it would just be, okay, yeah. Okay, so what we can do is if, I did not leave myself enough room for this, so let me move all this down. I hope that hides all of it. Yeah, now we can just move it down a bit. So, if I is equal to 0, what we do is just sum, or answer, gotta keep it consistent, answer plus equal to K minus 1, choose remainder, and that's basically it. Yeah, and then we just break. Yeah. Okay, so obviously to compute all of these fast enough, to compute all these, chooses fast enough, I will pre-compute the factorials, and yeah, that's basically the solution. So let's implement it. Okay, so first let's pre-compute the factorials. Oh no, why is it still running? Didn't want to keep that running. Okay, so vector int should be mint. Yeah, I'll be relying on my mint template, but it should not be too hard to just apply modular operations directly if you want. So yeah. So factorial should be 1, 1, 2, 3, 4, 5. And that should be 1. And then, in fact, we will define that in a bit. We will just directly use the in function on my mint template. Okay, so for int I is equal to I less than 1, 1, 2, 3, 4, 5, fact I is equal to fact I minus 1 times int of I, and then for int I equals to I less than equal to int of 5 plus I, and fact I is just equal to fact I dot inf. Great. And honestly, because we didn't directly define it, we're just going to start from 0, because why not? Okay, so now we have already deduced that we need to remove the extra from remainder, so we just do rem if sum is equal to 0, rem is equal to, rem just minus equal to k plus 1. K plus 1, and then what we can do is int answer is equal to 0 for int I is equal int I is equal to 0, I is less than equal to 2 plus. Yes, I forgot to mention this plus 2, this less than equal to 2 should actually be the minimum between remainder and 2, because we don't want to actually exceed the number for remainder. So if sum is equal to 0 and I is equal to 0, then what we do is we just do answer plus or equal to the factorial, mint fact k minus 1, and then we can multiply that by mint of in fact k minus 1 minus rem times in fact rem, and we can just break. Yeah, so now for int j equals 0, j is less than equal to remainder minus I over 2 plus j, j int singular is equal to remainder minus I minus 2 times j. Why is this giving, oh, it's a long. I might as well cast that to long anyway. So if s plus j is greater than let's just call it s, because plus j is greater than k minus 1, continue. If s is less than 0, continue. If s plus 2 times j plus I is not equal to rem, continue. Yeah, good. So then comes just this part, but we can just copy paste this in, copy paste this part twice, and then just change some variables, and we should be good. And then times that. Okay. So, okay, k minus 1, choose k minus 1 minus j plus s, and then in fact of just j plus s. And then this one is just j plus s, choose j, choose s, and then we can multiply that by what is it? I is equal to 1, 2, 1. And then we can just see out the answer, which is nice. So let's just test this real quick. I'm not completely confident that this will work, but we can debug if there's any error, or we can just submit it if there isn't. But yeah. Okay. 1 4 1 3 1 4 3. Okay, it appears to work. So now let's submit it, and hopefully it works. Well, I guess we still have to wait for the submit page to load, but that is a lot more chill than having to debug for 1.5 hours because you forgot that within the J+S you had to choose J. Okay, wait, can this load? Okay. Alright. Hope that everyone is having a great day so far. Yeah. And I hope that this editorial just provides some insight into a pretty fun and interesting problem. I need some page load. Yeah, okay, we're refreshing it. Cool. I'm just going to test 193. Okay, cool. Should work. Now this was actually an edge case that I failed a bit earlier. So yeah. Codeforces seems to be a bit slow, huh? Sometimes I have found that just opening a page twice seems to make the problem perhaps load a bit faster, so hopefully that is indeed the case. And I also hope that on the Division 3 tomorrow, when I open all these same apps, hopefully my computer will not crash or lag. Like, this is just lagging, isn't it? It seems to be lagging. Not letting me submit. Oh, now it works. Okay. Running on test case 1. Yeah, you can see like had some errors back down here, but hopefully we get AC this time without having to do too much debugging. Yeah. Okay, I think that this should pass now. Alright, very good. So yeah, the code indeed gets AC. Yeah, thank you very much for watching.